Today we finish the topic about instrumental variables. Let us start with the short repetition. What is this? What is the idea? What we are working with? Last lecture we spoke about several threats to internal validity. So meaning that once we estimate the causal effects of X on Y, the interpretation of this causal effect might be wrong because of several things. For example, the most popular problem is the omitted variable bias. We simply missed to include into the regression some variable that affects Y and is correlated with X. Another issue is the measurement error in X that might be a problem. And the third one is simultaneity bias. I showed you an example how the simultaneity bias occurs. And over the last exercise session, you were supposed to show mathematically that even in the population, when you estimate the coefficient, for example, for the demand elasticity, you will come to the completely nonsensical result. So even if you do everything kind of step by step, in population, you are not able to estimate the coefficient in a correct way. And we stated that there is an approach called instrumental variables regression that is able to solve these problems. The idea is very simple. You need to split your problematic variable X into two parts. In the first step, you do this division and you regress endogenous or problematic X on the instrument Z. This instrument must be some variable that is correlated with X and uncorrelated with the error term in the main regression. Then you obtain fitted values, and then you regress Y on these fitted values. So fitted values by construction are not correlated with the error term, and this X hat fitted values is exactly the component of X that is free of any of these three problems. This approach is used in several ways. So first of all, it is kind of popular in some empirical research when you want kind of scientifically to show the causal relationship between something and something. So suppose there is some economic theory. This economic theory claims that better education leads to higher income, for example. Of course, if you simply regress education on income, you will have omitted variable bias and you have a lot of problems. Why? Because first of all, maybe education is not, well, okay, so you can measure education correctly, but there might be simultaneity bias. So maybe if you earn more, you also can allow later on to study, to get some additional degree and so on. Why in principle it's possible. Another issue is omitted variable bias, because probably you have some ability, and because of this ability you kind of earn more and you study more. It is very difficult to measure this ability, because once you measure ability, you will get a measurement error, because ability cannot be measured kind of objectively, right? So it's always some kind of test, IQ test, whatever. Well, you see that in this empirical problem, you have simultaneously several, all of these threats to internal validity. And in such cases, people are trying to use something like instrumental variable to kind of, you cannot randomly force people to study like 10 years or 20 years or 15 years, right? It is not possible, because it is kind of, well, it's unethical to do such experiment with people. And for example, there is one research. I'm going to show you several examples of research, but since I started this, there is some research where people, like the authors of this research, they suggested a variable that is correlated with the years of study, but is not correlated with the income of a person. Guess what? What might be the instrument that is like the variable which is correlated with years of study and is not correlated with income of a person after the person got this education?
Age?
No, it's not age, but it's close. Like they took, as I remember correct, so maybe like there was some other idea, but if I remember correct, they took the following idea. So all people who were born in one year, like I don't know, in the year 1985, for example, there are two parts of the year. So people whose birthday is before September, they are admitted to the school immediately, right? So if your birthday is in June, you are like 7 years old and you can go to the school in September, the same year. But people of the same year whose birthday is, for example, October, they are not admitted to the school because in September they're still 6 years old and they are gonna be admitted to the school next year. The idea was something like this, if I remember correct. And then they used this birthday as an instrument because, well, okay, birthday is more or less random, right? So you cannot control birthday. But birthday influences how long you are gonna study. Like, well, when you start and when you finish, according to your age. So some people will finish school in like 18 years, and some people of the same age, they will finish almost in 19 years. Something like this. And then they kind of regressed the years of education on this birthday, like either before or after September, and finally they use these predicted values to regress income of a person on this fitted value. That's how it works. You see that like the application of instrumental variables with this sense is more or less special. You really need to do some empirical research where you're not able to make some experiments. On the other hand, these instrumental variables are used in the approach which is called generalized method of moments. We are not gonna talk about this. Well, I will think. So probably in the second part, we will slightly discuss about GMM because, well, GMM is a common method for working with the panel data, with time series, and this is widely applied in finance. But the idea of generalized method of moments is kind of complicated, and inside this generalized method of moments, there are also some instruments used to estimate the coefficients correctly. So I'll think about this. Would be a nice idea probably to briefly discuss about this method over this course, but not now. So now we move to the practical things, to the empirical things. We know the idea, we know what we are gonna do, how this works in practice. We start with the inference. Why? Because inference is very important. Once we estimated something, so basically all our discussion is about inference. Once you estimate some parameters of the model, we want to perform hypothesis tests, we want to know confidence intervals, and many other things. Here we have, if everything goes in the correct way, we have more or less familiar things. In large samples, the distribution of two-stage least squares estimators is normal. Same idea as in ordinary least squares. When you have large samples, you can approximate distribution of your estimator with the normal distribution. The inference, including hypothesis tests, building confidence intervals, is also the same as in OLS. But it is very important that the idea of instrumental variables regression is applied in a correct way. So instruments must be both exogenous and relevant. And this is the most important part here. We need to check somehow whether we have these exogenous and relevant instruments. This is additional dimension of hypothesis testing in the case of instrumental variables regression. But there is one important issue. Once you perform inference, you really need to know standard errors. Again, going back to Econometrics I, we said that standard errors are the estimates of variance of our estimator, and these standard errors they can be estimated in different ways. So we used heteroscedasticity robust standard errors because they are able to capture the heteroscedasticity of error term. And in panel data, we also used heteroscedasticity and autoregression robust standard errors. So in this case, in the case of two-stage squares,
didn't we use clustered errors in panel data?
Those are clustered errors, but those are like the, how to say, this hack estimator is a particular example of clustered errors, kind of.
Sorry, okay.
So both terms are possible in this case. So if you perform this regression in two stages and you simply take standard errors from the second stage of OLS, those standard errors are not going to be correct. I will demonstrate you. We don't take into account that x hat is a random variable itself, because x hat is based on the estimates of betas. Beta 0, beta 1 hat, if you have more betas, there are going to be more. So your fitted value depends on sample. And once you calculate standard errors in the usual way, those standard errors will not take into account this additional uncertainty related to the x hat. That's why I'm not going to the technicalities of the calculation of these standard errors. Those are beyond this course, but we need to remember that only the use of a specialized command in any software, so we are using Python, in any other software like Stata, R, whatever, you need to apply a special command, a special function to estimate coefficients of instrumental variables regression kind of in one step, and then it will produce you the correct standard errors. And of course, we need to use even here this heteroscedasticity robust standard errors, either HC0 or HC1, again, depending on our needs. So we usually by default we use HC1. So let us see how it works. Now let's try to apply instrumental variables regression and this idea to the practical application. Our empirical question is gonna be, is increasing the cigarette tax able to reduce cigarette consumption? So this is somehow related to the demand. can we increase in price of cigarettes, reduce the cigarette consumption? If you think about the practical application of this question, this is very widely used. So governments are trying to reduce the alcohol consumption, introducing something like excise taxes or some sales taxes or whatever. Governments are trying to reduce cigarette consumption by imposing some minimum prices on these and many other things. And the question here is, first of all, is there any causal link between taxes and cigarette consumptions? And more, let's say, narrow question is by how much demand on cigarettes would increase if you increase tax by, let's say, 10% of price. So definitely we need to estimate the demand for cigarettes, elasticity of demand for cigarettes, to claim then that if we increase price by 10%, demand for cigarettes would drop by 30%, let's say.
Like
yes,
log.
You remember correctly. So we are able to do that only when we apply log function. So in order to estimate this elasticity of demand, we need to use log specification in the following way. So we want to regress a log of quantity demanded on log of price, and we will get this linear model, log model. But we have discussed last time that the simple, straightforward OLS would not work. And you had the exercise session that mathematically showed that this is gonna produce incorrect results. So in order to estimate this, we have a panel data. We have an annual cigarette consumption in packages of cigarettes, as I remember correctly, and average prices including taxes. The data is collected in the US over 10 years period for 48 United States. And we propose an instrumental variable. Z is a general sales tax per pack in the state. The question is why this sales tax is gonna be a valid instrument. Let's try to think about this. Well, is this relevant? Is the covariance of sales tax and price is non-zero? I guess it's obvious, right? So the higher is the tax, the higher are gonna be prices. The more difficult question is this. Is sales tax exogenous to the quantity demanded? Sometimes people think in the following way. Well, if taxes increase, people buy less. This is a wrong way of thinking, because we are talking about your willingness to buy. And if you want to buy, what is included among the most important factors, what might influence the demand on some good? So when we studied consumer theory, utility function, all these things, and then finally we arrived into the demand equations. So these demand equations were functions of own price of this good, and what else?
Just a second.
For example, what can influence your decision about how many quantities of good to buy together with the price? What else?
Income, our income.
For example, income. Now the question is, your income, is this related to the sales tax?
No.
No, there is no covariance with this factor. What else? Prices on some substitutes. Well, if this is about sales tax, For cigarettes, maybe this is not correlated because prices of other goods will not respond. It's a very tricky question because prices of other goods might be somehow correlated with the price of cigarettes, and price of cigarettes definitely is correlated with the tax. But assume that those are independent. Consumer tastes, whether it's like trendy to smoke right now or not. Is this correlated with sales tax? No.
No.
Well, basically, most of the demand determinants are not correlated with the sales tax. After all, sales tax either so it probably it is paid by the producer. Sales tax might be the part of producer cost, but not the determinant of demand. So therefore, we can hope that sales tax is a valid instrument to some extent. So we will check it later whether it is truly valid or not. But at least we can hope. So reasonably, we can tell a story that sales tax is not correlated with other determinants of demand. And that's basically how any empirical research that uses instrumental variables proceeds. You need to tell a story. You are not able to formally check that there is no covariance because you don't know what is hidden in this error term. In our case, sales tax is not random. In the case of like a birth date, for example, birth date is random, so of course it is not correlated with anything else. But in the case of sales tax, it is not random, but we need to tell a story that, well, it is economically logical that this covariance is expected to be zero. Okay, so now we collected this data. There is a picture of the data frame. We have log quantity, we have log price, and we have the sales tax. In every state, we have different size of the tax. Somewhere it's zero. So basically, we have a panel data. It's balance panel. And this is another issue. So instrumental variables can be applied to the panel data. I'm not going to discuss technicalities of this application, but the idea is very similar. To make it simpler, just to abstract away from panel data application of instrumental variables, we will take only 1995 year, only 1 year, and make a regression. So we have 48 states. And here is the regression. We have the following coefficient estimates. We have p-values less than 0, so all of them are significant, but this is the first stage. So in the first stage, we regress price on the sales tax, log price on the sales tax. So basically, the interpretation is when the sales tax increases by 1 unit, price increases by 3.1% on average, right? We have log level specification here. This is significant. Therefore, we hope that sales tax is correlated with the price. Next is the second step. On the second step, we regress the fitted values of log price. We regress log quantity on the fitted values of log price. And here we have expected negative estimate of this coefficient, minus 1.08. But the standard errors in this estimation are not correct. Again, why? Because we performed this two-stage approach, but on the second stage we still had the usual OLS, and the usual OLS is not able to produce correct standard errors. So in order to do this, and we will study this function in on the exercise session, we need to apply another estimator which is called IV to SLS. So there is, you already know that there are many functions in Python that are able to produce some estimations. We have OLS. 2 weeks ago you used probit, you used logit, and now there is another function that works in a very similar way, and this function is called IV to SLS. You simply use this function, everything else is the same, and you produce the same result. You see that the coefficients are similar to the previous ones. So let's see, it was 9.7, 1.08, but let us note the standard errors here, 1.56, 0.33 approximately. And now we have different standard errors. So given the size of coefficients, even this small difference might be crucial for making statistical inference, because standard error here is smaller, and well, it might influence our decision about whether the coefficient is significant or not. And of course, we need to apply the heteroscedastic standard error in this case. So now standard errors are correct. Once we apply a special function in Python to estimate these coefficients. So, at least at this moment, the interpretation is the following. If we are able to increase price by 1%, quantity demanded will decrease also by almost by 1%, 1.1%. Right? So we somehow demonstrated that there is a causal link between prices and quantities. Well, detailed discussion is going to be performed a bit later, how practically to apply this. And traditionally, we will have some home reading to understand better the practical applications of this estimation. So, kind of summary of an idea of an instrumental variable regression with a single regressor. We need to always remember that a valid instrument must satisfy 2 conditions. One condition is relevance, the covariance between instrument and the problematic endogenous variable must be non-zero. So basically you need to believe, or you need to somehow claim and of course argue that this instrument affects the endogenous variable. And exogeneity. So an instrument must be not related to the error term, to all other factors affecting the dependent variable y. We proceed this two-stage squares estimation into 2 steps. First step, we regress x on z and we obtain the fitted values. Second, we regress y on fitted values. The idea is to isolate the part of the variation in x which is not correlated with u. And regarding the statistical inference, if the instrument is valid, in the large samples, we can perform statistical inference as in the usual OLS. Compare p-values with the significance level, desired significance level, or compare t-values with the critical values, like 196, for example, for 5% significance level. Any questions regarding the application of instrumental variables? No questions? Then we extend this model slightly. We will talk about the general instrumental variables regression model, when we have more than one independent variable and also some control variables. So the general regression model looks as follows. So we have k-axis. Those are, so let's also try to describe the notation right away. So y is a dependent variable, as usual. Betas are the unknown regression coefficients. So beta 0, 1, k, k plus 1, k plus r. Now we have, if you remember, we used the similar notation in the multiple regression model when x's were the variables of interest and w's were the control variables. Basically, this notation is very similar. X's are k endogenous regressors, those regressors which are potentially correlated with the error term. And of course, if we care about their correlation with the error term, those are the variables of interest. So we are interested in the effects and the causal effects of these variables on y. W's are included exogenous regressors, if you believe that some of these regressors are not correlated with error term, or they might be just control variables. We don't care whether they are correlated or not with the error term. We simply include them to control for some factors. Idea is the same as in the multiple regression model. And we have an error term. Might be now, it might be a measurement error, or it might be the effect of some omitted factors. And also we need to have a set of instrumental variables. And look, we have a set of m instrumental variables. So basically we have k endogenous regressors. We have r, it's not k, it's a wrong notation here. We have r control variables, and we have m excluded exogenous variables, which are instrumental variables. Now we need to introduce an important concept in not only in instrumental variables, basically in many other fields of econometrics, which is called identification. So identification is related to a parameter. So in our case, parameters are betas, the coefficients. So a parameter is identified if different values of this parameter produce different distributions of the data. We spoke about something similar in mathematical statistics, and you must remember that if we have a parameter and this parameter somehow changes the distribution of the data, this parameter is identified. If we have two values of parameter that produce identical distribution of the data, you are not able to identify parameter. So think about this. Basically, we are going in the opposite direction. We get the data, and based on this data, we are trying to estimate a parameter. And there is kind of like one-to-one relation. A data is uniquely generated by a value of this parameter. If the value of parameter changes, the data must be different in principle. Like, remember the method of maximum likelihood. So we are trying to derive such value of a parameter estimate that maximizes the probability to observe exactly this sample. So now think about the idea when the same data might be produced by two different parameters and both of them have the same likelihood. You will not have a choice which parameter value produces this data. So the parameter is not identified. And related to the instrumental variables, it means the following. So in instrumental variables, identification of coefficients depends on the relation between number of instruments and number of endogenous variables. And this is very simple. If there are fewer instruments than endogenous regressors, we cannot estimate betas. So at least every endogenous variable must have one instrument. Like if you have two endogenous variables, you must have at least two instruments. You can have more, but at least two. If you have three endogenous variables, problematic variables, you must have at least three different instruments for each of these independent variables, and so on.
Sorry, but isn't the exogenous variable is the problematic one?
Endogenous one. The problematic is endogenous. Exogenous means that exogenous variable is not correlated with the error term. Exogenous variable is okay. Endogenous variable is correlated with error term, and this is not okay. So we can call the coefficients beta 1 to beta k exactly identified when the number of instruments equals to the number of endogenous x's, problematic variables. There are just enough instruments to estimate betas. We call coefficients over-identified when we have more instruments than endogenous variables. And this case gives us a nice opportunity to check instrument validity. So you see that basically we need to tell a story that instruments are valid. But if we have an over-identification case, we can formally test that these instruments are valid. It is called the test of the over-identifying restrictions. And the worst case is when we have under-identification, when the number of instruments is less than the number of endogenous variables. In this case, we have no other choice just to obtain more instruments to have at least exact identification. Because otherwise you will have a multiple choices for betas. Your estimate of beta might be like 2 and 10, and you will not be sure which one is closer to reality. This is just a repetition of what we have discussed in the case of a single regression applied to the general instrumental variables regression. Suppose we have one endogenous regressor, and suppose we have a set of exogenous or control variables, these W's. How the estimation is performed? So we have M instruments for only one endogenous variable. And on the first stage, we do the following. We regress X on all instruments and all control variables. This is very important. We are not doing regression only on instruments. We include in this regression all available exogenous variables, both excluded instruments and included, with W's. So this is the most important difference between the basic single regressor model and this one, general. This is called the reduced form equation for X. You can remember because this term reduced form is used in many applications. When you read some papers, you can find this term. Then, with the help of this regression, we can compute predicted values of X, and then we regress Y on X head and W's with the help of OLS. Again, we regress Y. Instead of X, we have X head, and Y is regressed on the set of control variables. As before, if we perform this in 2 steps and both of these steps are using OLS, standard errors are wrong, but estimates are going to be correct. So therefore, we need to apply this IV to SLS function in Python. In any other software, the functions might be different. So let us apply this to the example. As Vlad said, another omitted factor that affects quantity demanded for cigarettes is income. So we can explicitly include income into this regression equation. And also we can use this as a logarithm of income to have income elasticity. So if income increases by 1%, how much percent quantity demanded increases? And we can use two instruments. One instrument is a general sales tax, and another one is cigarette-specific tax. So you can think about this like in the Russian setting, for example, you can think about value-added tax, which is applied to all goods, and excise, special excise on cigarettes. So taxes, cigarettes have two taxes applied to their prices. So endogenous variable is log pi. This is what we called x in the previous model, and included exogenous variable is income. Why it is exogenous? Well, we don't think that income is related somehow to the error term. Might be, but well, we cannot. Or at least this is a control variable, right? So we don't care much about the income elasticity, because as a government we cannot change income. Well, in principle, we can give something like a subsidies for people to smoke, right? So instruments, two Zs, general sales tax and cigarette specific tax. Which case do we have? Is the demand elasticity over-identified, exactly identified, or under-identified?
Exactly identified.
Think better. How many endogenous variables do we have?
Endogenous, then over-identified.
It's over-identified. Yes, we have only one problematic variable, and we have two instruments to help with the identification. Well, this is the result when we use only one instrument. So we start with one instrument, one endogenous variable, and here is the estimation result. So let us first look at p-values. The estimate of log income is not statistically significant. So I guess it's reasonable, because income does not affect the demand for cigarettes, right? So poor people, rich people, they can smoke the same quantity, or maybe, well, this quantity does not. If your income increases, you probably don't smoke more or less. This is reasonable finding, and still log price has a positive result. So here we estimated this in one with the one function. So no two stages, no first stage, no second stage. We report already the result estimated with the help of two-stage squares here, and you see that elasticity is slightly increased compared to the single regressor model. So it was 108 before, now it's 114. So that's exactly the case of omitted variable. And when we include two instruments, still the elasticity, income elasticity estimate is not significant. But with the help of two instruments, we have even larger estimate of the price elasticity here. So what are the so we can compare one instrument, two instruments results with two instruments. Elasticity is in absolute terms, of course, is higher. So cigarettes are more elastic, like the estimate of this.
I have a question. Like a theoretical one. We had a model where we maybe in self-study or home assignment, where we came to conclusion that higher the education of a person is, less he smokes. And also we covered like the model where the higher education like brings more income. But here we have that income is not dependent on education. Wait, sorry. Smoking is not dependent on
Smoking
income.
doesn't depend on income, yes.
But what about those two previous models?
That's a nice idea to start another paper, show one paper, show another paper. Look, in this paper, authors showed that smoking decreases with income. That's chain of
Education
conclusions
with
that you said.
education.
Yes, so smoking depends on education, education depends on income. In this regression, we see that income does not influence quantity demanded. So what is the reality? We perform another study, right? So basically, that's how ideas for papers, for scientific papers occur. You compare results of one study, another study, third study, and then there is some contradiction in the data, in the results of that study, and finally you come to some interesting conclusions. So, in short, income here is a control variable. We don't care much about this estimate and whether it is significant or not. Because, as I said, maybe income in kind of in a very detailed way, if we try analyzing income, income might be correlated with the error term. And income is not truly exogenous. Because income might be correlated with the taste of a person. Maybe like richer people prefer healthier life and they smoke less. And this is about consumer tastes. Poor people, they probably don't care about their health and they smoke more. And moreover, they have some maybe stress, and because of the stress, they smoke more. Maybe I can tell you another story like smoking is very fashionable. There is something like a social smoking, and people like rich people can smoke more because of like in their society it is more acceptable. Well, I don't know, but like in principle, we cannot claim that this estimate is truly correct. We just don't care, because as for with any control variable, we include this because we know that income is a determinant of quantity demanded, but we are not interested in this estimate as the true causal effect. So we can find some other instrument to use here, and probably it is gonna be statistically significant, and even the size of this effect will be different. So that's why probably it's not a good idea to compare those results with these results. Different samples, different studies, but again, if you want, you can perform your own study, you can compare approaches there and here, and you can come up with some outcome that will finally kind of join both results together. Back to our question. We have smaller standard errors for the case where we have two instruments. See that for all coefficients, standard errors are smaller. This is not irrelevant, because when we use two instruments, we obtain more information. We have more kind of as if random variation. So that's why the standard errors are really lower. We have low income elasticity, which means that this is not a luxury good, but on the other hand, this is income elasticity is not significantly different from zero. And what is surprising here, that there is a high price elasticity. Why do you think it is surprising? What does it mean economically?
Like higher price, less consumption.
Yes, but this is the usual case for any demand function. For any demand function, you expect that larger prices lead to lower quantity demanded, unless you have a given good. We also introduced such type of goods in microeconomics classes. If there is a given good, higher prices lead to higher quantity demanded. But this given good is not kind of, it's something strange. In this case, we have a negative sign. This is okay. Negative is what we expect. Regarding price elasticity, it's about the size of this coefficient. There are elastic goods. There are not elastic. Like there is elastic demand and not elastic demand. What does it mean?
There's more than one.
Yes,
the
we need to compare this with one. And what are not elastic goods or goods with not elastic demand?
Is when it is less than one.
In absolute value, yes, but economically, what does it mean?
Like,
for example, which goods have low price elasticity from our everyday life?
low price elasticity. Like how to say that? First need goods, like needed goods.
Well, maybe. Yes. Those goods which you will keep buying, and it doesn't matter for you what the price is. You really need to buy them. So one popular example is gasoline. Well, no matter what the price of gasoline, you still be filling your car because there is no substitute. Well, in principle, you can buy an electric car, but to substitute a usual car with an electric car needs high costs of this substitution. So that's why, well, if you have a car and if the prices of gasoline go up, you still have you still have to fill your car, and you still will be buying almost the same quantity of gasoline. And basically, it is believed, usually in economic theory, we also give an example of cigarettes as a good with a low elasticity, because if you are a smoker, you have a habit to smoke. And it doesn't matter for you what is the price. If the price goes up by 10%, well, you still consume the same amount. I mean, it is believed. But now, data says that the price elasticity is, in absolute terms, greater than 1. So, which means, once you increase prices by 10%, people drop their consumption by 13%, almost. This is elastic good. It's still not clear. We still have some place for discussion. Is this a correct estimate of a causal effect? But this is a nice observation, because we have something which contradicts the economic theory. We can extend the general model with k endogenous regressors. Now I will move through this slide very fast, because the idea of this model is the same. Before we had only one endogenous regressors, now we have k endogenous regressors. What happens when we have more than one endogenous regressors? We have k first stage regressions. Every in endogenous X must be regressed on W's and instruments x1, x2, and up to xk. And for every first stage regression, we obtain fitted or predicted values of x. X bar 1, x bar 2, blah, blah, blah. And finally, when we have the full set of fitted x's, we move to the second stage regression. We regress y on x1 head, x2 head, xk head, and the control variables. In the empirical research, you will rarely see such case. I saw the regression with 2 instrumental variables and 2 endogenous variables. Maybe there are other papers, but not much. As usually you are interested in the effect of one particular variable. But in general, we can perform instrumental variables on any set of endogenous regressors. The last question here that we need to discuss is how to check an instrument validity. So an instrument is valid when there are 2 conditions held. Instrument must be relevant and instrument must be exogenous. So we have a general form of instrumental variables regression. There are some assumptions for these instrumental variables regression. First assumption is familiar: conditional mean independence. Conditional on control variables, the expected value of an error term is 0. That is why we include these control variables. Observations of all these variables, so don't panic looking at this vector of variables. You have many variables here: yi, x1i, x2i, xki, blah, blah, blah. So what is this vector? This is kind of one row in your table of data. Like every row in your table is independently and identically distributed. That's simple. All of the variables used in this regression, x's, w's, z's, and y, have non-zero finite force moment. So it means that there are no outliers. Familiar assumption. W's are not perfectly multicollinear. Control variables must not be perfectly multicollinear. And the instruments, this is additional assumption for instrumental variables, because first 4 assumptions are the multiple regression assumptions. The instruments are valid, which means that there is an instrument relevance condition. X's and W's are not perfectly multicollinear. Well, there is some issue with these signs. I don't know what has happened. Must be x1 star, x2 star, w's. And instruments are exogenous. So covariance of every instrument with the error term is 0. When these assumptions hold, 2 stageless squares estimator is normally distributed, and it gives us a chance to perform a statistical inference. So we need to check these 2 conditions somehow. We need to test them. So first of all, how to check an instrument relevance? Well, instrument relevance is when instruments are correlated with the problematic endogenous variables. When we look at the first stage regression, when we regress X on the set of instrumental variables and control variables, the instruments are relevant when at least one of these coefficients from P1 to Pm are non-zero. This is very obvious, right? Because if you are able to predict X with the help of at least one Z, you're okay. What do we need to do? Well, further terminology. We call the instruments are weak if these pi's are 0 or nearly 0. So, because weak instruments explain little of the variation in X. Now the question is how we can test that how we can test that at least one of these p's is non-zero. This is a familiar instrument. We know how to work with that. We performed those tests many times. How we can check that at least one of these pi's.
Joint hypothesis.
Correctly. We need to perform a joint hypothesis test, and this hypothesis is gonna be what? That all pi's are 0. And if we are able to reject this hypothesis, it means that at least one of these pi's is not 0, and instruments are valid. So we call totally irrelevant instruments when all coefficients are 0, and we test this joint hypothesis with the help of F statistic, right? This joint hypothesis is tested with the help of F statistic. But now, look, now we have a nuisance. It is not only about rejecting or not rejecting the null hypothesis, because look, we are also interested. So instruments might be weak. It means that statistically, one of these pi's might be different from 0. But it will be very, very close in statistical terms to 0. That's why we don't want to use weak instruments. And there is a rule of thumb, kind of approximate thing. We compare F statistic in the first stage with 10. This is like a practical issue, right? So in practice, when F statistic exceeds 10, then we are fine. If F statistic is less than 10, then the set of instruments is weak. And we need to find better instruments for our case. Yeah, so if F is less than 10, the estimator is biased and statistical inference is misleading. We cannot rely on confidence intervals, on hypothesis tests from the second stage regression, when F statistic on the first stage is less than 10. Well, basically this is simple. We have a first stage regression. So this is the part of the Python code. We test the joint hypothesis. You must remember how do we do this. This is like either F test or something like that. And we see that from the first stage regression, when we had only one instrument, F statistic is 42. When we do, well, I didn't report the first stage separately. So basically, in principle, you can perform the first stage. You can have the same table with the regression output. And in that table, you can also find F statistics. So I decided to do this using the other way. And yeah, sales tax is a relevant instrument. We can regress log price on sales tax and cigarette tax, so 2 instruments, and obtain from this also perform here the F test, and the F statistic here is 247. So you will review this code on the exercise session. Now it's just an illustration that when we have the set of 2 instruments, F statistic is even larger. It's 247, so both sales tax and cigarette tax are the relevant instruments. We cannot reject the hypothesis that both instruments have 0 coefficients. If F statistic is less than 10, we're in troubles. Why? If we observe this simple formula for two-stageless squares estimator here, what do we have in the denominator? We have covariance between x and z. If this covariance goes to 0 in population, the estimate of this covariance also goes to 0. And when this goes to 0, you see what happens with the beta hat. Beta hat inflates. And of course, the distribution starts to be far from normal because, well, since some variable goes to infinity, definitely normal distribution cannot model something that goes to infinity. This is a simple illustration. Why do we care about relevance of the instrument? And why do we care about weak instruments? Even if this covariance is close to 0, but not 0, we are still in troubles. So how to solve this issue? Find better instruments, or if we have many instruments, we need to drop those instruments that are weak. Luckily, in our case, we have both instruments relevant and not weak. Or we can use a different estimator. But this is not what we are going to discuss here.
Why?
Because I cannot include everything in one course. We just need to concentrate on something most important and most common, unfortunately. So
Very sad.
you can study econometrics for 10 years and still have something new. So we need to do the most classical things. But I promised you that I will think about GMM. I didn't include this in the last year course of Econometrics II, so now probably I will try to prepare something, and this is another way what you can do, another estimator. So I'll think about this. So this is the way how we can check instrument relevance. First stage regression, obtain F statistic, compare F statistics with 10, and then make a decision whether instruments are weak or not. Second property of good instrument is instrument exogeneity. And with an instrument exogeneity, we have a trouble because, as I said, the correlation of instrument with an error term can be justified telling the story. Like I told you the story that quantity demanded does not depend on the tax itself. Sorry, not quantity demanded, but determinants of quantity demanded, like tastes, income, and all the other things are not related to the sales tax. And unfortunately, in some cases, we cannot do more, but in some cases we can. Well, the problem is that when instruments are correlated with the error term, X hat is going to be correlated with the error term, and that's it doesn't solve the problem, the initial problem that we wanted to solve. We wanted to break this link between X and U, and if instruments are correlated with U, it doesn't help. And we can test this condition only in the case of over-identification. In the case when we have more instruments than endogenous variables. If parameters are just identified, we just need to tell a story and justify this with the help of logics. Otherwise, if there is over-identification, we can do that. So let's take the simple case. We have one single endogenous regressor and we have two instruments. The idea is to compute two separate estimates like we did, and then if the estimates are very different from each other, so the question is, what does it mean, very different? Then something must be wrong, because, well, it cannot be true that using different instruments, we have different, very different estimates from each other. So it's either one or both of the instruments are invalid. And in this case, like formally, we can perform the J-test of over-identifying restrictions. So we can give it like some precise form in a way how we test, how we perform some statistical tests. So what do we do in order to apply this J-test? So first we estimate the equation of interest using two stageless squares and all M instruments. We already did it for cigarettes demand. Then we compute the predicted values of Y hat using actual axes, using actual observed values of independent variable. Then we compute residuals. All the steps must be familiar to you from the first econometrics, nothing new here. And then we regress these residuals against the set of instruments and control variables. What do we have in principle? We check whether error terms, like error term estimates, because residuals are estimates of error term, are correlated with these variables when we perform this regression. And how can we do this? So in principle, what do we want? We want all coefficients to be 0. All coefficients on all these variables. In this case, U hat is not correlated with either of these variables. So we compute F statistic for testing this joint hypothesis. And then there is a J statistic. J statistic is M, number of instruments, multiplied by F. And this and we have a null hypothesis when all instruments are exogenous, so when all coefficients are 0 jointly, against H1, at least one instrument is endogenous. And then we are in trouble, because if one instrument is endogenous, it's not a nice thing. And under the null hypothesis, I don't formally prove it, J statistic has a chi-square distribution with m minus k degrees of freedom. So we can have two tests to check instrument validity. One is the first stage regression, F statistic compared with 10. In this sense, we can test whether instruments are relevant. And when we have more instruments than endogenous variables, we can perform this J-test over identifying restrictions. From the second stage regression, we obtain residuals, and we regress residuals on instruments and control variables. Again, we obtain F statistic for this and multiply by the number of instruments to get J statistic. J statistic has a chi-square distribution. You will do all the steps on the exercise session to obtain the same results as we have on the lecture. So in our empirical exercise, we can test the exogeneity only for the regression with two instruments. So this part is the regression with two stageless squares. So we regress log Q on log P, sales tax and cigarette tax, and log income. You see, well, you will discuss this special way how we write down the formula. You see that this part, the first stage regression, is kind of nested inside the second stage. Then look what we do. We obtain residuals from this regression. It's here, so you know how to obtain residuals. And then we regress residuals on two instruments and control variable log income. Finally, we test the joint hypothesis that both coefficients on sales tax and cigarette tax are 0, and we get the following F statistic, 0.17. Now we multiply this 0.17 by 2 instruments, and we need to compare this J statistic with 97.5 quantile of chi-square distribution, which is 5. So this is something like 0.34. This is 5. Test statistic is less than critical value. We cannot reject the null hypothesis that all instruments are exogenous, which means that we believe that instruments are valid. Finally, they are relevant. First test, and they are exogenous. Second test. And just a reminder, how do we calculate this chi-squared? Well, guys, the last thing that I wanted to discuss with you is about some practical issues, and I wanted to show you the illustration about two research, like two papers that used these instruments in practice. So I will upload these lecture slides on the course page, and you will look there. Well, basically, there is not much to say. Well, why do we have two similar slides here? Yeah, I will check. There must be two. So I will skip this part. Your home assignment in your usual way. Section 12.4 from Stock and Watson. There is some extended empirical discussion of this example about demand for cigarettes. Quiz that is based on two lectures about instrumental variables and this section 12.4. The quiz is, what is that? Oops, sorry. So, reading, self-study on instrumental variables regression. Quiz number 4, based on the lectures 5, 6, and that section from Stock and Watson. Again, it must be the typo. It's till October 12th. So let's check. Not 11th.
Yes, it is until October 12th. I checked it.
Okay, as usual, because I gave you usually time till October, till like days after. Yeah, but it would be nice if you perform this faster. And home assignment number 4, estimation of instrumental variables, available till next Tuesday, October 18th. Questions? So today's lecture was more intense than usual.
No questions. So we have a quiz until